This video tutorial shows how to get started with Vega Thejaz 32 core implemented on DG-Lent RDA 735T FPGA board. At the end we will try to make a digital magnetic compass with this setup. The overall procedure mentioned in this video is typical and can be applied for other boards supported by CASP. We presume that DG-Lent drivers and Vivado software were already installed on the host PC. Let's start by uploading Thejaz 32 MCS file and creating a test program. FPGA board was connected to COM10 serial port of host PC. Open CASP and install Swadeshi board support package. Restart CASP to update board support package documentation. You can go through the hardware configuration of Thejaz 32 and 64 and can do modifications if required. Programmer 0 is configured to upload the hex file via X modem. And Programmer 1 is configured to upload the program to FPGA flash memory via Vivado. So, configure Vivado bin path accordingly. You may go through the Vega board support package documentation as shown. Let's us now program the board with a simple LED blink model. We choose LED 0, red LED, for blinking. Serial port issue. It seems our setup is working properly. You may observe the red LED blinking as modeled. Now we will try for serial debugging on Vega. For this, we will use existing tutorial project on custom block with user code. We will try to add printfs and monitor them from CASP running on host PC. Please refer to our video tutorial on how to create a custom block with user code. Load the custom block project and delete unused blocks. The block with plus symbol is the custom block with user created code. We have earlier added printf statements in this block code only. For serial debugging to work, we may need to upload the program to FPGA flash memory. Also, set debug level to 2 or greater. There is some problem during program uploading. Programmer 1 was not able to find bitstream file in project directory. Copy the thejaz32.bit file to project directory and try again. It may take some time to upload. Set the boot select switch to off and then press prog button to refresh the board. Serial debugging seems working. Set boot cell switch to on again and press prog button to prepare for next step. Now we will try to control a servo from user code using CASP HAL APIs located in the BSP library folder. The root file is vega.h. CASP HAL APIs resembles Arduino Core APIs. This allows users to use them without learning a new API. We will use Servo class in our custom code to control the servo motor. We will create a logic to sweep the servo from 0 to 180 degrees. We use PWM2 pin for servo. Use CASP GPIO pins internal ID when using them in the code. Hope this logic works. Here is our setup with servo control pin connected to PWM2 of TheJAWS32. Arduino board is used to provide plus 5 volts to the servo as FPGA board electronics is having some EMI issues. Build the model and program the board. Servo sweep logic seems working. Now we will try to interface MPU9250 and W5500 with CASP on TJAS32. We will use MPU9250 to make a digital magnetic compass. The steps shown are generic and are applicable for other capable boards supported by CASP. Typical schematic is shown here. TJAS32 will acquire the required magnetometer data from MPU9250 and sends to the host PC through W5500 Ethernet communication. The received control signal from host is used to set servo angle. Here is our setup. The MPU9250 is mounted on a servo. The expected logic is that the servo has to follow the magnetic north. This logic will be developed on host PC. Later on, user may transfer the logic to FPGA board as shown in our previous video tutorial. Avoid loose connections. Let's start by creating model for FPGA board one by one. We will first try to establish communication with CASP running on host PC via W5500 Ethernet link. We will send and receive 16-byte data. Map the pins accordingly. Configure tap out to extract first 4 bytes of received data as float data type. Configure servo limits from -90 to +90 degree. Adjust simulation settings to non-real time. Seems internal pin IDs of GPIO and PWM are clashing. Better use pin labels in that case. LED is blinking. That means W5500 is working properly. We will try to establish communication from host. Configure CASP native application hardware I/O to communicate with W5500. The 16-byte data from target board is treated as 4 into 32-bit integer or float data on CASP native application. Board seems communicating with cycle time of around 700 microseconds, which is pretty decent for a soft core. We try to give some commands to control the servo. Servo control seems working. Now try to connect with MPU 9250. The MPU 9250 outputs magnetometer data of XYZ planes. We require all 3 for our analysis. Configure data tap in block to insert three 32-bit integers, XYZ data of MPU 9250, in the 16-byte data stream starting at index 0. Build and upload the model to the FPGA board. Red LED is blinking. That is both MPU 9250 and W5500 are working properly. If any of these doesn't work, LED will not flash and user has to investigate the cause. Seems our target board is sending magnetometer data. Let us control the servo parallelly. Now let us build the magnetic compass control model on native target. First we plot the received data for analyzing. We are now seeing the real-time data from the magnetometer. We try to see the variation in the magnetometer XYZ values with respect to the orientation. For this, we try to control the servo manually. Please note that if you are using an evaluation version of CASP, then target board may halt after some predefined time as per license. You may reprogram the board to start again. It seems X value is changing sign when it is aligned with magnetic north. This we will use it for designing our control loop. We will try to design a closed loop so that the servo aligns with the magnetic north based on the magnetometer X data. We try to tune PID parameters to get desired response. It seems our magnetic compass is now working with some minor oscillations when the field becomes stronger. Observe that without an external magnet our compass settles towards geomagnetic north. Thank you for watching this video.